Okay, well this week we're going to talk about biomedical imaging. And you know from the first lectures I mentioned that one of the biggest advances in biomedical engineering was the development of systems for looking inside the body. And that's what we're going to talk about this week. Sort of what's the physics behind some of these systems, how do they work, what are their limitations, and what are the opportunities that each of them present. And again, like almost every week's subject, this one could take up a whole course. In fact, there's 3 or 4 courses on biomedical imaging that are offered here at Yale. So we're just going to scratch the surface of it. But what I hope to do is give you some sense for how these different modes of imaging work, why they allow you to see inside the human body, and then what the limitations of each particular technology is. So these are the kinds of questions that I hope we'll be able to answer by the end of this lecture and next lecture. What is an image? Most of you could answer that probably now, but images come in different forms. And why is imaging so important to medicine? You probably already know, either from what you've read in the past or from your own experience. Most of us have had, at some point, by the time you're as old as you are, you've had an image taken of your body, a medical image, usually an X-ray. So you know something about why it's so important, but we'll try to amplify on what you already know. What technologies are available, and so we're going to survey the different techniques that can be used and that are used most commonly. It's a very rapidly developing field, and almost every year there are new innovations in imaging, sometimes even new methods that are introduced. That change the way we can see inside the body. And so I'm going to talk about sort of a snapshot of what's available now, and as I said, illustrate or talk about what some of the problems are or challenges with each. What are the limitations in particular? So an image is a visual representation of, can you get the door again? Sorry. It's become a routine thing for us. A visual representation of some measurable property of a person, an object, or a phenomenon. We're going to be thinking about medical imaging, so we're going to be thinking mainly about images of people. And images can be formed and displayed in different ways, depending on properties of the object and properties of the imaging system that you're using to create the image. And so you're familiar with certain kinds of images. You've all probably taken a photograph with a camera. Photography has changed dramatically since you were born, right? It used to be all on film, and now it's almost all on digital. And so these are different ways of capturing the same thing. A photograph is a representation of what you can see. It's a representation of how visible light reflects off of objects. And so you see the outlines of the objects and their colors and their textures, but it's basically a representation of how visible light is interacting with some object. An X-ray, on the other hand, shows you something that you can't see on your own. It allows you to see inside the body. And this is because it's not using visible light, which bounces off of objects like us, but it's using X-ray radiation, which is able to penetrate the body. And so by taking a picture of how these particular form of electromagnetic radiation, called X-rays, by taking a picture of how it penetrates through the body, you can get an image that represents something about what's inside. And the challenge is to know, because you understand the physics of the radiation, in this case X-rays, and you understand the equipment that's used to collect the image, you should be able to interpret from your understanding of those things what it is that you're seeing inside the body. And of course, television is a different kind of image, presented in a different way, but another image of something that we can already see. So 2 kinds of imaging, really. Images that represent to us, maybe not exactly the way we see it, but things that we can see. And images that represent to us things we can't see, but put it in a form that we can interpret. And so that's just what this says here, that some images you're just trying to collect and record what it is that you can see so that you can look back at it later and remind yourself of what it was that you saw. Other imaging systems are really transducers, right? They're converting something that you can't see into something that you can. We talked about transduction several weeks ago now when we talked about cell communication. and the concept of transduction, converting one kind of a signal into another. In this case, converting a signal that measures something you can't see, but converts it into something that you can see. So to understand this, I have to review for you something that most of you probably already know, at least at some level, and that's the electromagnetic spectrum. And this is a representation of the variation in properties of electromagnetic radiation. And certain forms of electromagnetic radiation are apparent to us because our retinas can detect it. And that's the visible part of the spectrum, which I've shown here. Now, what this shows is the entire electromagnetic spectrum arranged on a scale from very short wavelength up to very long wavelength. And these are in centimeters. The visible part of the spectrum is around a micron or so, or slightly less than a micron. Right? It's around 400 nanometers to 700 nanometers is the visible spectrum. Now, why is this the visible spectrum? Because when radiation with this wavelength hits your eye, it makes a change in the cells inside your eye and allows your retina to make an image. Right? So it's only light of those particular wavelengths that can interact productively with this particular special biological object called the retina. And that's all the light that we can see. But there's electromagnetic radiation of all different wavelengths outside of the visible spectrum. In fact, one of the things you should notice here is that the visible spectrum is only a small piece of the entire spectrum of electromagnetic radiation. And you know this already. There are longer wavelength. There's longer wavelength radiation called infrared. So it has wavelengths that are longer than in the visible spectrum. You can't see these, right? But some cameras can see infrared, right? That's how when you watch the films from the war in Iraq, where they have these sort of heat visualization goggles, they're looking at infrared wavelengths. So there's something in the goggles that is sensitive to infrared light, and it converts it into visible wavelengths, which you can see. Right? Have you ever seen satellite pictures where they used to do this? Oil companies or electric companies would take a picture of neighborhoods from the sky, right? Infrared. And infrared radiation is associated with heated objects. So the higher the temperature of an object, the more infrared radiation of a higher wavelength it emits. So if you take a picture of a neighborhood at night using an infrared camera, you can see how much heat is being emitted from all the different houses. And you can identify ones that don't have enough insulation, for example, or ones that are wasting heat because they're emitting it at a higher temperature. So these are some examples of using a wavelength that our eye can't detect, but getting information from it. You also are familiar with ultraviolet radiation. So these are wavelengths that are shorter than the visible spectrum, shorter than the part of the spectrum that you can see, but you can experience the effects of ultraviolet radiation. Right? If you're out in the sun too long, your skin turns red. Right? You get a sunburn. That's because your skin absorbed ultraviolet radiation, created a change in the cells of your skin. Right? Different biological effect. You're seeing it in a sense. Right? You're only seeing it where the sun hit, not where your body was in shadow. Right? But you can detect that radiation that way. So if we look at the whole spectrum, I'm going to go back a slide now. And this was arranged with the long wavelengths up at this end, the short wavelengths down at this end. The other picture is arranged in just the opposite way, with the long wavelengths down at this end, radio waves, microwaves, infrared waves, the visible spectrum, ultraviolet, X-ray, and gamma ray. So these are long wavelengths proceeding to shorter wavelengths. As the wavelength changes, so does the frequency. They're inversely related. So as the wavelength goes down, the frequency goes up. And the frequency is related to how much energy these waves contain. And so the short wavelength, X-rays and gamma rays, carry high amounts of energy. Right? Ultraviolet rays carry more energy than visible rays. Right? So frequency goes up as wavelength goes down. and so does the energy of the radiation. This diagram here shows you roughly how big is the wavelength. So for radio waves, these are very long waves that are the size of buildings or bigger than people. Microwaves are shorter, they're the size of an insect. Infrared waves, shorter than that, the size of a pinpoint. The visible rays, the ones that our retina can detect, are about the size of cells. Bacteria, for example, or protozoa. Ultraviolet rays, the size of molecules. And then X-rays and gamma rays are submolecular. They're subatomic in size. And because of that, they have special properties in that they can actually change atoms. When X-rays and gamma rays are absorbed into materials, because their wavelengths are smaller than the wavelengths of atoms or nuclei, they can actually interact with atoms and nuclei. And one of the things that X-rays and gamma rays can do that other rays don't is ionize an object. They can actually eject electrons from the atoms inside of a material and create ions. And the ions that they create are often reactive. And this is what makes these short wavelength, high energy forms of radiation biologically hazardous, because they are in the category called ionizing radiation. When they hit your body, they can produce changes, in particular produce atoms, or ions from atoms. These ions can further react. Sometimes they even react with DNA inside cells and can cause mutations in DNA as a result of chemical reactions that occur. And because of this, we want to limit the exposure of our bodies to things like X-rays and gamma rays. I'm going to talk about, in the course of the lecture today and tomorrow, many of the ways that X-rays and gamma rays are useful for medical imaging. And that's not surprising, because I already said these are short wavelength, high energy forms of radiation. They can penetrate through objects fairly easily. So things that penetrate are useful for imaging what's inside. But the disadvantage of their penetration is that they can also create ions and biological damage. So we'll keep that in mind as we go through. You know that not only ionizing radiation causes biological damage, but I also mentioned the biological effects of overexposure to ultraviolet light, which you've probably all experienced through sunburn or some other overexposure. So these aren't the only kinds of rays that can have a biological effect, but they're the ones that we're most concerned about. Okay, questions about that? Or this is probably a picture that you've seen before. If not, I encourage you to review review sort of the physics of the electromagnetic spectrum. Okay, so let's talk about X-rays, and that is the form of medical imaging that's been around for the longest. Before X-rays, as your chapter in your book describes, physicians and doctors relied on hand drawings. They would draw things so that they could describe what they saw to others, or so they could remember if a patient came in and had something abnormal, they might draw a sketch of it in their notebook so they would remember how it looked for next time. And then photography changed that, because you could take pictures of things and you could remember them without drawing. But we still couldn't look inside the body, right? Still couldn't look inside the body. Well, you could, but not really very well on living people. Right? So a lot about what we knew about the inside of the body was from the science of dissection and looking inside the bodies of cadavers, people after they died, and learning about their anatomy that way. So we knew something about that, but we weren't able to look inside a living body. Well, this Wilhelm Röntgen changed that, and Röntgen was a physicist who discovered that X-rays could penetrate through solid objects. And he announced that discovery in 1895. He did an experiment which is shown in a diagram in your book, where he put objects in front of an X-ray source, and he was able to show that these X-rays would pass through the object and he could detect them on the other side with a film. So here's two useful properties of X-rays. One is they can penetrate through solid objects. The second is that they can expose film. film, like photographic film, is sensitive to X-rays. And because of this, then you can imagine taking a picture of how these rays pass through a solid object. Now, the other thing that's interesting about X-rays is that they pass through some solid objects better than others. The more dense the object is, the less radiation, X-ray radiation, that passes through. So if you expose an X-ray beam on an object that's solid at some parts and hollow in the others, X-rays are going to pass easily through the hollow part and not so easily through the solid part. And so the amount of X-ray radiation that goes through an object is related to the density through which that X-ray penetrated. And it's these properties that made it good for taking images. After he discovered that that X-rays could penetrate through objects, it didn't take him very long to say, well, if it penetrates through solid objects like bricks and boards, maybe it'll penetrate through a person as well, and took some of the first images, X-ray images of people by looking at the hand, for example. And he won the first Nobel Prize in physics for that discovery. And so it was one of the things you could take from this, from the time that he first announced it, 1896, till the time he won what's come to be known as the highest prize in science, took only 6 years. So people recognized immediately the value of this approach, particularly this approach for medical imaging. Now, the ray that he discovered we now call the X-ray. Initially, it was called the Röntgen ray because he was the one that discovered it. And there are some countries that still refer to X-rays as Röntgen rays. And so you might hear that nomenclature if you travel or if you're reading, particularly in older textbooks. So how does it work? Here was the first kind of experiment that I described earlier, an X-ray source here. The X-ray source is emitting X-rays in all different directions. Some of them would impinge on this object, right? And depending on the density of the material within inside this object, some of the X-rays would be absorbed and some of them would pass through. In a dense part of the object, the X-rays would be absorbed. In a less dense part, more of the X-rays would pass through. And if you put a piece of film or some kind of a detector behind the object, then you could create basically a shadow, right? Just like a shadow when you're standing on the street and the sun is up here, the light doesn't pass through you, and so what you see on the ground behind you is the sun all around, but a shadow where your body did not allow the radiation to pass through. In this case, you'd see a shadow of this object. But it could be a more sophisticated shadow in some ways because the X-rays can penetrate somewhat through dense material and even better through less dense material. So the shadow would be light where there was density in the object, and it would be dark where there was hollowness or less density in the object. Right? Makes sense? So in this way, an X-ray is a shadow. It's an inverse image of the density through which the X-ray passed. The diagram over here shows you a more sophisticated setup and the kind of setup that's used for X-ray imaging in patients. So you have an X-ray source, and so X-rays are emitted from this source, and if you didn't confine those X-rays in some ways, they'd be emitted in all directions. But you confine it so that X-rays are only emitted from one side. You let that pass through a filter because these sources of X-ray generation are not perfect. They generate waves of different wavelengths, and so through a filter that only lets X-rays pass through a device called a collimator. And a collimator is a physical object that basically just straightens out a beam. If I had a source of radiation here, right, and it was emitting X-rays, they would radiate in all directions. I could put something that was X-ray dense behind it, and now they would only emit to the front. But what I would like is if I want to take an image of someone, if I want to take an image of me, for example, I would like all those X-rays to pass straight through me so that I knew what direction all of the rays were traveling. So that when I tried to interpret what was on the film, there'd be a one-to-one correlation between where the X-ray hit the film and where it went through my body. If I've got X-rays coming from all different directions, then that's going to blur the image, right? So you need to straighten it out so the X-rays go in one direction, and that's what a collimator does. It's shown as a hole here, but really it's a sheet with many small pinholes, and these pinholes only allow X-rays to go through if they're going in the right direction. Right? Ones that come at an angle like this are going to bounce off, but X-rays that come straight through are going to pass straight through and hit the object. The object is the patient, so I'm standing here, and there's something behind me that's going to detect the X-rays that pass through. That something behind is this. There's a grid also to prevent scatter, to only collect the X-rays that are passing in the right direction, because some of those X-rays might have been deflected as they pass through the object, through me. Right? But I only want to collect the ones that are going in one direction so that I will know where the anatomical object they pass through are. That hits a fluorescent screen, and the fluorescent screen is a special material that emits light when X-rays hit it. So an X-ray hits the fluorescent screen, it generates a lot of light right in that spot, and this detector detects the light. So the fluorescent screen amplifies the X-ray signal. Several photons of X-ray hit, they generate fluorescence, they expose the detector. And now, in the old days, this used to be really film, X-ray film, photographic film that was sensitive to X-rays, and the detector was really a piece of film that you would take out of the machine, and you would develop it with chemicals, right? The same way you develop any other kind of photographic film. Now there are detectors that are electronic, and so you can detect things electronically without film. If you have an X-ray, though, you probably, if you have one at home, a chest X-ray that your parents gave you, say you're going off to college, take your chest X-ray. Anybody bring one? Well, if you did, it would be probably a real piece of film. Right? So X-rays are formed from high energy radiation. An inverse shadow is created because X-rays pass through less dense areas easier. And what's it going to pass through in the body? If you do a chest X-ray of my chest, for example, where will the X-rays pass through the most easily? Well, they'll pass through the lungs. The lungs is primarily air, right? The lungs is air and tissue, but it's mainly air spaces. And so what you see as dark here are the less dense regions, are the lungs, where nothing much interfered with the X-rays passing through the body. Right? Had to pass through skin, soft tissue, some muscles, and then primarily through air. Where the image is light here, those are regions that absorbed most of the X-rays, so not many of the X-rays got through to hit the film in back of me. Right? And those areas appear lighter. So this bone, the clavicle, appears light. The ribs appear light. The bones of the rib cage appear lighter. What's this object here? In the chest, over on this side, big. The heart, right. And why does the heart appear light on this image? Well, it's not bone, right? It's not as dense as bone. It's muscle, it's soft tissue, but it's also filled with water, a lot of water, right? And it's a three-dimensional object. And so for X-rays to pass through this whole three-dimensional object, a lot of the X-rays get absorbed, right? It's a thicker object than this bone. And so even though it's not as dense as bone, it appears whiter here because it's thicker. Right? And X-rays have to pass through more of it in order to get to the other side. The thicker the region it has to pass through, the more opportunity for those X-rays to be absorbed. The diaphragm. And what do you think are these scattered sort of white things all around here? All around the side here? Well, first, what's this object that comes up and sort of off to the side? Here's the heart. Something comes up. Sorry? The aorta. The aortic arch is here. Remember from our pictures of the heart? You can't see it entirely because behind it is another white object that's sort of in the midline here. That's the bones of the spine. Right? And in this region here, they're all superimposed. Right? So you can't really tell how much of this absorption comes from the aortic arch and how much of it comes from the spine. So this is one problem with X-rays, that you're not seeing a three-dimensional image of the chest in this case. You're seeing a projected image, right? And so you're only looking in one direction, really, and you're seeing a projection of all the things that the X-rays could pass through. So I can't tell, for example, if the aortic arch is in front of or behind the spine. I can't even tell where the boundary of them are because it's all just, they're absorbing X-rays, and so I can't see it. So what if I wanted to look at this in more detail, or I wanted to distinguish what part of this is the aortic arch and what part is the spine? How would I change the imaging? Sarah? Yeah, you could ask the patient to turn to the side, and you could then do the same measurement this way, right? And now you'd see another projection, but you see a projection from another angle. And so you would be able to differentiate what is different in this direction, right? And you might do it obliquely. You might ask the patient to turn, a little bit sideways, or turn the other way. And by putting together several different images taken from different angles, you can learn more about the three-dimensional aspects of what's inside. You might be able to see things that you can't in one image in one of the other angles. Okay? So X-rays are a projection, a two-dimensional projection of a three-dimensional object, and that's one of their limitations. And you can get around that a little bit by by moving the object around and taking images from different sides. Another problem with X-rays is radiation dose. I mentioned that X-rays were a form of ionizing radiation, and so if you're exposed to X-rays, you could be generating ions inside. And with a normal chest X-ray, if you only have one chest X-ray taken every 5 years or 10 years or so, the dose that you get is relatively low. Your body has mechanisms for repairing that biological damage, right? Your body has mechanisms for repairing the kind of biological damage that's done by ionizing radiation. And so if the dose is low enough, the risk of some permanent kind of damage is fairly low. Where there is a risk is if you have repeated exposure to higher doses, in which case you're generating more ions are being generated in your body than the repair mechanisms that are naturally in place can repair. And then you get tissue damage. And so one is concerned when you're using radiation with limiting the dose that is delivered on each X-ray. So how could you reduce the dose here? How could you reduce the radiation dose that the patient receives? Thinking about how this thing works, how could you reduce the dose? Well, one is you could use the minimum number of X-rays necessary to see what you want to see. And of course, as you use less radiation dose, you're going to see less on the image. So the sensitivity is going to go down. And so one of the things you might not see if you use less radiation dose, you might not see these other structures here that are barely visible in this particular image, right? And these structures here are vessels from the pulmonary vasculature and the bronchi associated with the lung. And you might care about those. So you might need a higher dose in order to see what you want to see. So you can reduce the dose by reducing the intensity of the radiation, but the cost is you don't get as high a quality of an image. Not as useful for diagnosis. Right? One could also make innovations in the machinery, right? In particular, you could make detectors that are that get more sensitive. And the more sensitive the detector is, the more information you get per per photon or per radiation. So more sensitive detectors allow you to make better measurements with less radioactivity. And there have been those innovations continually over the years. And so the X-rays that you would get now are fairly low dose X-rays without much apparent risk to you. You also can limit where the X-rays hit the body. And part of that's done by focusing, part of it's done by something called shielding, right? So if you were getting a chest X-ray done, they might put an apron on, right, at your waist. That apron contains a very dense material, and so the X-rays don't penetrate through below your waist, right? So these are all ways that radiologists use to reduce the radiation dose to patients. We talked about being able to see more by looking at different angles. And the technology called computed tomography, or CT, is sort of the end product of that. It's trying to design X-ray machines, and CT machines use X-rays. The physics of how you form the image is exactly the same. You're generating X-rays, and they're passing through the body. What's different is that the machine allows you to take pictures at many, many different angles while the patient stays still. So instead of asking the patient to move from one side to the other so you can take pictures at different angles, you have an X-ray source and a detector that basically spins around the patient. And it takes pictures at different angles. And you use not a broad beam that's going to expose my chest all at the same time, but you use a narrow collimated beam, a narrow beam that you can focus and move throughout all of the angles around the body. So you're not giving a sort of a plane of radiation anymore. You're giving something more like a line of radiation, right? And as that line passes through me, there's going to be absorbance detected back here, depending on what was in the way of that particular line of radiation that was coming through. Now, any one line doesn't give you very much information, right? Any one line of radiation doesn't give you very much information. But what if you collect those lines from all around my body? You can basically see my body from every angle. That still is going to be a complicated set of images, right? What if you took 360 pictures as you spun this thing around my body? Now you got 360 pictures to look at. How do you make sense of that? Well, you couldn't really. And so what really made CT possible is that mathematicians figured out mathematical ways for taking all of these separate images that are collected as you move around the body and reconstructing an image of the whole object that must have been in between. Right? The mathematical process is called back projection. You take a large number of projected images that are acquired from all different angles, and you can reconstruct a picture of what the object must have looked like that it was sampling. Okay? Now, because it's a narrow beam, you're doing this in a line instead of a plane, and you're spinning it around. You're really doing a slice through the body with each rotation of the device, right? If I spin this all around my body, then I'm basically moving this line around different angles, and I'm looking at one slice, maybe between here and here, all the way around. And so you can reconstruct an image of a slice that might look like this. Right? The chest X-ray, a plane of radiation, shadow of what that produces. The CT gives you a slice, a transverse slice of the body, but it shows you the real three-dimensional structure of what's inside. So what can you see in this picture? Well, here was the spine in this picture. Is this from the thorax that contains the lung, or is this from the abdomen that contains the intestines? Don't read the bottom of the picture. But just looking at it, it's not the lungs, right? Because you don't see a lot of dark area in here that would indicate air. Right? What you see instead are a lot of soft tissues that sort of absorb radiation. This here is the liver. You can see muscles and bones of the rib cage, which are down in the abdomen here. You can see the spine very clearly. You can see the kidneys at the back. You can see the intestines in here. Right. And so an experienced radiologist who's looking at this can see a lot of information arranged in the proper three-dimensional way. Now, this is one slice, but you could do another slice as well. And you can do that in the machine because the patient is sitting still and is moving through the machine one step at a time. Right? So there's a conveyor belt here that's bringing the patient into the machine. And in the machine is this rotating array of X-ray sources and detectors. This part spins around. So you bring the patient in, you spin it around, you collect all the images, you bring them in a little farther, you spin it around. Each time, each increment that you move the patient in, you're taking a picture of another slice. And so one could take a three-dimensional image of the whole body. Now, because you're just using line sources of radiation, one can reduce the amount of radiation that with each individual picture that you take compared to an X-ray, but you got to take a lot of these pictures, right? And so the cumulative dose of radiation can be significant. So even though you could take a full three-dimensional picture of your body, you might not want to do that, right? You might just want to take a picture of the slices that seem to be of interest. Maybe the abdomen, maybe the chest, maybe the knee, if you're having a problem with your knee, right? And so CT is commonly used for head injuries. It's fast. It's very effective at detecting blood in the brain, for example, so you can detect that easily. And for analyzing the structure of bones. And you know X-rays are very good for bones. If you've ever had a broken bone, then you've probably seen an X-ray of the bones of your body, and that's because bones absorb X-ray radiation, and so X-rays are very good ways to detect it. I think that's where I want to stop for today. And we talked about X-ray radiation. I've got some slides on here that say a little bit more about ionizing radiation. And I put them on there for you to read because it's not in the chapters in the book. But this talks about sources of ionizing radiation, a picture of sort of what it is, and some of the biological effects of ionizing radiation. It's sort of beyond what I'm going to ask you about in the exams or anything, but I wanted you to have that information. And then next time, we're going to move on and talk about forms of imaging that don't require X-rays and so don't have the biological risks of ionizing radiation. We'll talk about ultrasound imaging and MR imaging, and we'll talk about what I think is going to be an important imaging technique of the future, but using light to image inside the body as well. Okay, questions? Good. Thanks. I'll see you on Thursday.